All right, hi guys, welcome back. It is day 8. We are still on chapter 6, exponential growth. We have moved on to example 3. Okay, so now we're gonna get into what I think is like the most interesting part of exponential growth is like the real world application of it. Okay, a lot of things that have to do with population of accruing money and value all happen exponentially. Okay, so you'll see a lot of those problems being modeled in this section. So we're going to take a look at the population of a city, and we are going to actually create the exponential growth model for it, and then we're going to use that model to solve for what the population is going to be after a certain amount of time, okay? So the important thing to start with is that we have our generic exponential growth model and that we break down what that means, okay? So typically we start with A times B to the x, all right? And so the y is going to be your answer, right? When you plug things into this value and you get an answer, that is going to represent your final value, okay? So when you plug in all those other things, they are going to give you the final value, whether that's a population, whether that's money in your bank account. That's what you're solving for when you plug in things for A, B, and X. A is your initial value, okay? Initial means beginning. It means like your original value. So again, that could be the population that you start with. That could be, number of animals in a habitat. That could be a deposit in the bank. That's whatever you're starting with. B is your growth value. We've talked about that before. I'm going to break that down more in a second. That tells you, whether you're growing or decaying and by how much. And then your exponent represents time, okay? But we really need to break down this B term, okay? So B is, in fact, your growth value, okay? And typically, we're not going to always see it as just a number B. We're going to open it up and we're going to say that B can either be 1 plus R, or B can be 1 minus R, okay? So that's 1 plus the rate if it's growth, or it can be 1 minus R, which is the rate, if it's decay, all right? And we're going to talk about that more in a second, and it'll make more sense what that means, okay? But the important thing is your R is your rate as a decimal, okay? As a decimal, which means if you're given a rate as a percentage, let's say, they told you that something you were getting interest at 28%. 28% is not a decimal, okay? Remember, to go from percents to decimals, you want to take that decimal place and move it to the left, okay? So then this would be 0.28 as a decimal, okay? To the left. All right, and so again, if you had 7% as a percentage, you move that 1, 2 to the left. Remember, anytime that there's a space, you fill it with a 0, okay? That should be like middle school knowledge coming back at you, okay? So 7% would be 0.07 as a decimal. The best thing, though, is that it's really, really easy. Do that in a calculator. If you ever need to find a percentage to a decimal, just divide it by 0. So let's say you had 56%. You would just type in 56 divided by 100 in your calculator, and it will give you that decimal correctly every time, okay? So you can also divide by 100 for percentage to decimal. All right, so now that we know our anatomy of this problem, we know what everything means, where everything goes, now let's look at our problem, okay? So it says the population of a large city was about 4.6 million in the year 2010, grew at a rate of 1.3% for the next 4 years. If the population continues to grow at the same rate, what will the population be in 2040, okay? So going through this problem, we found a lot of good information, okay? We saw that the initial population was 4.6 million. That's our A term, okay? That's our initial value. We're starting this problem. We didn't start apparently taking population until 2010, so that's our initial, is 4.6. It says it grew at a rate of 1.3%. That grew is really important because that tells us that we're going to use this guy over here because it's growth. And so I need to know 1 plus r, what's that rate? They give it to us right here, 1.3%. We know 1.3 divided by 100 is 0.013. So we're going to be using that as our decimal for rate. And so now the trickiest thing is we know our A, we know our B, our X is time, okay? And so what's tricky here is it's telling you that it grew at a rate of 1.3% for the next 4 years, okay? That's good. That shows us that the rate is stable. It's not changing. But the question says if the population continues to grow at the same rate, what will the population be in 2040? Okay, our answer to time is actually in this part of the problem right here. Okay, so let's start filling things in. We do not know what the final value is. That's what we want to know. We want to know what the population will be in 2040. Okay, so y, whatever that final population is, equals my initial population. I know it's 4.6 million, but I'm just going to leave it as 4.6 and then remember that my unit is millions. Times, now instead of writing B, I'm going to write 1 plus R because that's my growth value, okay? So anywhere that I see B, I can rewrite this 1 plus R or 1 minus R instead. So I'm going to say 1 plus 0.013. And now X is time, okay? So the question doesn't say what will the population be in 4 years. If it said that, then X would be 4. It says if the population continues to grow at the same rate, what will it be in 2040? So now that's my question. What do I put for time? Do I write 2040 for the time? Do I want to know what the population is going to be 2040 years after we found out that it was 4.6 million? Okay, the answer is actually in the comparison of the years, okay? So if it was 4.6 million people in 2010, and I want to know what the population is in 2040, it's actually the 2040 minus the 2010 that tells me that I'm measuring the growth of the population after 30 years, okay? So my time is actually 30. And then the best part is once you're here, you just throw this all in a calculator, okay? So remember, I recommend the Calculate 84 app. I think I've mentioned it in all the videos. Also Desmos, also the TI 84 software is available online, okay? So make sure you're looking up one of those. I'm going to go to my calculator. Again, I'm so sorry that I can't rotate this for you, but I'm just going to do 4.6 times 1 plus 0.013 to the 30th, and then hit enter. And then we'll round this, and so we'll say that that is 6.78. So we'll say that y equals 6.78, meaning that our population in 2040, in 2040 is about 6.78 million people. And that's your exponential growth model, okay? So remember, the things that will change are going to be your initial values. Maybe it'll be money. Maybe it'll be something different. Just make sure you're looking to see if it's growth. If it's growth, make sure it's 1 plus the number. If it's decay, it'll say things like the population was decreasing or it was getting smaller. It might actually say the word decay, and that's when you would use 1 minus. Please remember, divide by 100 anytime you're looking at a percentage to get it as a decimal, okay? But you guys should be able to take it from there. Let me know if you have any questions, comments, concerns. Google Classroom, Remind, email. I check them all every day. I just sit by my computer waiting for you guys to talk to me, okay? I love you so much. I miss you guys terribly. Yeah, I hope you have a wonderful rest of your day. Goodbye.